like and leave a heart, please.
There we go. Hello, everyone, and welcome to the Vidor Locksmith Show. I'm your host, David Gibson, where we are unlocking the secrets to success in the oil and gas industry. One interview, one technical presentation, and one technical screw-up at a time. So happy that you guys are here with me on this beautiful Friday. It's been an absolutely amazing week, and we have a lot in store for you today. Really excited about this presentation, as well as today is the Central Texas AADE Zoo Night. So first ever family zoo night. So if you guys are going to be coming out to that, please let us know. Give us a shout out here in the comments. Gibson Reports will be sponsoring the Yuletide photo booth. So if you guys take any photos there tonight, it'll be brought to you by the amazing team here at Gibson Reports. Like I said, been an absolute amazing week. Had a lot of fun. Really excited to be able to get the show on the road today. So let's go ahead and give a handful of people a shout out here that are watching. Let us know where you guys are watching from. You know, all of the normal stuff that we do on Fridays. So first up, as per normal, is John DeWart. Good morning from home of Road America, the National Park of Speed. Absolutely excited about that. Would love to be able to get out there and race on that track if I ever get the chance. We got Eric tuning in. It says hello from sunny south of France. Thanks for being here, sir. And as ever, Ian says good morning from the Woodlands, Texas. Thank you, sir, for being here. A little bit slow on the comment side today. That's quite all right. I know we still got plenty of people out there watching. Is everything coming through on the LinkedIn side there, Tracy?
Yes.
All right. Oh, and then we've got, here we go. Charlotte Adams says, good to see you again from Texas. Charlotte, thanks for being here. Do appreciate it. Isabel says, hi from Midland. There we go. Andrew says, good morning, David. Good to see you again as well, sir. Oh, and then the ever-present LinkedIn user from Thailand. The LinkedIn user, like, man, they travel a lot. Always getting around. Former guest here on the show and entrepreneur galore there. Kate says, good morning from OKC. If you guys haven't checked it out, be sure to go to wellbuilder.com. Wellborebuilder.com. Go check it out. Amazing software. To be able to help you with your wellbore diagrams. I learned a lot during that episode. So big thanks to Kate for coming on the show and talking about it. So yeah, if you haven't seen that episode, go back and check it out. It was like, what, 3-4 episodes ago, something like that, Tracy. And then John says, viewing from low country, South Carolina. Okay. Hopefully he's getting some good barbecue while he's out there. Takamedov, Mr. Takamedov, I think it's the best chance I got to pronounce it was from Turkmenistan. Wow. All right. I think you're probably one of the first tuning in from Turkmenistan on the show. Thanks for being here. Ricardo says, good morning. Thanks for being here. LinkedIn user John is on LinkedIn geosteering Austin Hall country. Oh, Austin Hill country. Oh, John, you're in the Hill country. Hey, come stop by sometime. Come see us. All right. At least he knew he was going to come up as LinkedIn user, so he put in. Andre says, "Good morning from OU and Norman campus." Well, thanks for tuning in, guys. All right. As per normal, let's do the thing. So this week's show is brought to you by the amazing team. Oh, hold on. Go back to comments. Click. There we go. Banners, brand. There we go. This week's show is brought to you by KeyDrill. So put in hashtag KeyDrill into the comment section now for your chance to win. Oh, wow. There's so much stuff. I'm dropping it all over the place. We got a USB stick. Yep. KeyDrill USB stick. Hold on. I got to make sure I hold it at the right distance so it actually comes into focus. KeyDrill USB stick. Arctic cup. KeyDrill hat. These guys do not come short on the swag. KeyDrill pin, koozie, hold it the right way, notepad. I actually really like these. Those are pretty nice. A KeyDrill shirt, and my desk is getting loaded up with tons of stuff, and a Gibson Reports drill bit. So put hashtag KeyDrill into the comment section now. Also, throughout the entire show, to be able to get your chance and entered in to be able to get all of this swag, maybe even potentially more because it's, Christmas time. And watch this quick video from our sponsor. Thanks, guys.
KeyDrill is at the forefront of MWD technology. Driven by ongoing research and development, our systems are built to be rugged, modular, and customizable, meeting the specific needs of the industry. This dedication has positioned us as leaders in MWD system design and production.
I need to take this. But yeah, hashtag KeyDrill, put that in, get you a chance to win some awesome stuff. Oops, I hit the wrong button there. Brand. Nope, that's still not the right one. Hold on. Getting lost in my thing. Haven't been doing this enough. All right. Just want to give a shout out to Mr. Dicky Hall. If you ever want to be on the show, sir, I would love to be able to have you come on the show. But thank you for putting the hashtag KeyDrill. Appreciate that one. All right, guys, let's get on with the show. So today we have an absolutely amazing guest here with me today. We'll go ahead and put, there we go. Let's scroll over just a little bit. There we go. Nathan Zenero is here with us to be able to talk about, how would you say it?
Bit grading of the future.
Bit grading of the future. Thank you so much for being on the show, sir. I do appreciate it. I will turn it over to you now. So let's go ahead and put this, or here, when it comes, nope, that's not the right one. There we go. There. I'll step out of the way and let you take over and give us the rundown of
Absolutely
what it is that we're talking about today.
Yeah, so I want to start with a story of why we're doing this at all, because that's really lays the foundation for what we're trying to accomplish here. We're not grading bits for the sake of grading bits. This isn't technology for the sake of technology. And it's really a human-centric story that we're trying to tell and a human-centric problem we're trying to solve. So click here.
We'll go back over there. There we go.
Yeah. So, how we got it all started. I was a drilling engineer at Chesapeake Energy for a while. We were running a lot of rigs at the time, 170 plus. So we had lots of opportunities for technical screw ups, like you mentioned in the beginning, right? We learned from more than one technical screw up at a time. And one of the basins I was working in was the Mississippi line, right? We were famous up there for DBR'ing about every third or fourth drill bit, right? So running 16 rigs in the Miss line, DBR'ing every fourth drill bit, hundreds of millions of dollars of loss in terms of just tripping. And then not to mention, I didn't know drill bits could get destroyed the way that we were destroying them, coming out just shiny stumps of steel, or the most interesting cores out or ring outs that you'd see. I've seen pictures of cored out bits on, you can Google it and you can find them, but those pictures have nothing on how we were destroying bits, right? I'm an engineer and I can think my way through it. And I said, guys, I know chert's hard. Chert's a 20 KSI rock, but I also know that we manufacture our diamonds on our drill bits to 2 million PSI, right? That's what we're compressing them to. So it seems like we have a couple orders of magnitude difference problem between how we're damaging our drill bits and how they should be able to perform in that rock, right? So we started looking at all the data. I say I was kind of a one-man band for a while on this project. I got 2 terabytes of data from all the wells we drilled over a few years up there. So 146 wells worth of data, not a small data set. And that was 432 lateral bit runs, right? So every DBR bit that we had encountered over the period of 3 or 4 years was included in this. So the lessons we were able to learn from this were going to be pretty concrete, right? If the statistics panned out and there was confidence in it, we knew that it was going to be a very high confidence level. And so we started this project and said, no one's ever done anything like this before. And there's a lot of degrees of freedom, right? We could look at, a million different dimensions of how we want to analyze data. But really to do it, we have to make the data set smaller in a way, right? So we have to take a bunch of data that we have, combine it into one thing, kind of like if you're modeling flow, you have Reynolds number. If you have Mach numbers, you have these dimensionless parameters that let you look at things apples to apples, even when they might not appear as such. And so we did that with this. We took all of our bit grade data and our dull grade data, and we said, okay, let's make that into like one number. And it ended up being a number that came out between 0 and 64. So the bit grade itself, the 0 to 8 was part of that, but then there were text comments. We mined those and said, okay, if it's got ringed out in the comments or some variation of that, because people spell things weird, right? If it's cored out or some variation of that, or, so we looked at, the natural language part of that. And we came up with a score that was, 0 was a perfect bit, and you would think, and we'll get to that in a minute, but you would think that if someone puts zeros on their bit, that it would be green bit. But there's a surprising number of zeros that also had ringed out in the comments, right? So either they were just not grading it at all because why put the numbers there if it's ringed out, or they were messing up the 0 to 8 and thinking that 8 was highest score is best score, right?
I could see that.
And so we also looked at the physics of this and said, let's look at the energy I'm putting in axially. Let's look at the energy that I'm putting in from my motor. Let's look at the energy I'm putting in from my rotary system. And let's look at like other frictional losses to see if that's a contributor to it. And then let's compare that to the actual strength of the rock that I'm cutting, right? And so what that let us do is say, okay, well, fortunately for us, mechanical specific energy is in units of PSI. Wonderful. So is my rock strength, right? And so now I could look at something like absolute efficiency, right? To see how much energy am I putting in versus how much energy I needed to cut that rock. And so we could say, what is actually the driver of this? We wanted it to be, process driven, physics driven. We wanted to understand what was causing these. And you would think, the common understanding in the Miss Lime was that, hey, you're drilling through hard rock, you're drilling through chert. That's a cost of doing business is to DBR your bits, right? And we could prove pretty clearly at that point that wasn't true, right? The frequency of a DBR bit was directly proportional to if they were drilling efficiently or not, right? The higher efficiency you had in drilling, the less likely you were to DBR a bit, right? Or to have a high damage score for that matter, right? And so we could actually make plots that showed a linear relationship between that 0 to 64 score and the absolute efficiency of a bit run. And so when we started to rank these sort of things, we saw that, what were the principal components that were contributing to bit damage. And at low bit damage, having efficiency was like kind of related to having low bit damage, but it was a weak relationship. And things like, weight on bit and the high RPM, so weight on bit thresholds above, 20,000 pounds or something in that basin was considered, we set as high. Or high RPM, but you could see like a low efficiency score was not as dominant of a factor in my bit being damaged, right? But the more damage I saw in my bit, the stronger the relationship between low efficiency and high damage became, right? And so the answer was not, clearly, the answer we could say without a doubt, the answer is not the cost of drilling in chert is DBRing bits, right? We knew that if we drilled more efficiently, we could get longer bit runs and perhaps even one run laterals, right? We just had to learn how to drill efficiently. Other things we noticed out of this, though, were some problems with process, right? So 35% of our bit grades had gross errors. By gross errors, I mean they had zeros marked in the IADC dull grade,
Okay.
but they had ringed out, cored out DBR, right? And so either we are like completely flipping the scale or we're not putting the data in. But either way, if the only thing I looked at was the IADC dull grade, I would have not been able to do this project. The data would have not made sense at all. All right. The other 50% had confounding errors where comments, or if there were pictures available, which was very rare for us at the time, they did not necessarily correlate well to what actually happened. So the comments, maybe they did grade it, maybe there wasn't all zeros, but it would be ringed out, it would be twos, right? So like it's not flipped, but somebody is not, putting in the grades correctly. And so that highlighted an issue, right? Now we have a human problem, we have a process problem, right? And so what do? Do we just let people write comments and we'll sort it out with some machine learning, or do we teach people how to do this better? What's the real answer? And so we, you like that? We called in some big guns. Our first call was Fred Dupriest. We brought in Eric Van Oort from the University of Texas to give courses on drilling efficiency and process efficiency, so that our drilling engineers could learn that it's not about mashing on it to get more ROP, that there is a science to solids transport, to vibration mitigation, to treating your bits better, right? And the first thing that Fred told us was the first thing you got to do, if you don't do anything else after this, he gave us 2 or 3 days of his time. The first thing you got to do is take a picture of every bit. And we said, okay, and to me, that's like, finally, right? This is something I've been pressing the organization for a long time. How can I, as an engineer, know what's going on if I don't have data at my disposal that's reliable and that is consistent and that gives me an ability to differentiate between, drilling vibrations and bad bits, right? So that's the thing that he said. He said, to start taking pictures of your bits. So a group of engineers at Chesapeake took it upon themselves to start to write a manual for how to take pictures of bits. And you've got some nice cameras in here. You understand a little bit about photography. And so they made a manual that was 42 pages long, had 12 sets of instructions on how to select the right focus and ISO settings and where to set the bit at the different times of day so that you didn't get shadows. And what it really meant was there was a 0% chance that this was going to happen, right? And we can do the quick mental math, right? At 172 rigs at the time we were running, and you've got 4 company men and a partial superintendent on every rig. Let's just say we have 4.5 people. We're looking at 650 to 700 people that we would have to train to do this. Not only was the manual just not workable, we'd have to train and retrain and retrain and retrain all these people to do this, right? And I said, this is not a good idea, right? There's probably a better way to do it. And I enjoyed our little conversation earlier about building things for prison grade at FedEx, because my mind immediately said, first my mind said, I have more respect for the men in the field than to give them this sort of task to do, right? Because we want them to do other things. To be perfectly honest, they should be doing other things. But it's bad for a couple of things. This was going to only support still a manual grading process. So the IADC put together a bit grading symposium in Navasota at the NOV research facility about 1.5 years ago. And they put like bit manufacturers, directional drillers, like people that have significant expertise in grading drill bits and had done it in the field and in the lab for long parts of their career. And so they split us up, 4 people into 10 different teams. So they had 40 people grade these drill bits, all the same bits in the same room at the same time. And what we saw was, even among that group of people, significant variability, right? 60 and 70% variability in the grades that were given to these, right? And this is from the experts. And so again, 0% chance of success, because if we expect this much variability from the experts, we should really expect more from company men, right? Or from directional drillers, or from whomever, because they're in a worse environment, right? The expectation is not as high for them to be experts in that particular process, and they have 20 other things they're doing at any given moment, right? So that was one thing we understood. I also understood that this 0 to 8 methodology and this kind of encoding of certain information in the way that IADC does it is flawed in and of itself, right? So if we want to put this in a database, we want to use it for data science purposes, it really is not well formed, right? You cannot do cutter by cutter grading with this, right? You can barely do section by section grading of a bit. You can only describe like one kind of damage per section when really there could be, multiple present. And it only lets you talk about like very coarse levels of damage, 12%, right? And if you want to do some data science, it'd be nice to have continuous increments of data, not these big chunks, right? So even using that methodology, if we were to take pictures and we were to, have somebody that's just like the bit grading guy who looks at back in Chesapeake's campus, the likelihood of us being able to grade these in a way that our bit manufacturers could use to improve design or that we could use to improve drilling practices was really low, right? Thinking again too about, and maybe I hit the table.
No, it's all right.
About, when a bit gets graded, right? I mean, there's the old kind of running joke in the oil field, cement cures best under moonlight. So when do bits come out of the hole, right? Probably the moonlight before, right? But also when that bit comes out, what are they doing? They're taking down BHA, they're racking back pipe, they just finished a trip. There is so many other things going on that necessarily take precedence over grading that bit, right? Safety is number one, operational continuity is number two, operational performance is number three. Somewhere like number 93 on the list is, get French fries for dinner, grade the bit, right?
Yeah.
Maybe, right? So
check in on the MWD hand after that.
There you go. I mean, and so we're asking these men to do what should be a key engineering task that shouldn't be in their purview. Number one, we're asking them to do it at a time when they have so many other things to do, right? And also, what is the cost to them if they don't do it, right? If you went and hollered at a company man, hey, you didn't grade your bit, he's going to let you know that he's got better things to do and he's going to be right every single time.
He's going to tell you where the sun doesn't shine.
You know it. So again, this is a people problem as much as it is a process and technology problem. What some people do is they'll farm that out. They'll have the bit hand come by and grade the bit for them, or they'll have the DD do it, or they'll have somebody else.
Yeah. Let the bit hand do it. And
grade his own bit.
Grade his own bit, and then most likely that could have been one of the causes to the 000s, because it's like, oh look, this thing graded
perverse
all
incentives.
Zeros,
yeah.
But then it's like, oh, we'll put in the text box, which can't be just like filtered through as easy. It's like, oh yeah, it's wrung out.
And
so
just as a general rule, and I'll say this about anything, this goes for BOP testing, this goes for mud motor inspection, pipe inspection, bit inspection. The people who are responsible for supplying it or manufacturing it should not inspect it, right? That is a conflict at all the time. No matter how much you trust them, it's not if, but when that conflict will arise. And other industries don't allow it, right? There's independent inspection of critical components, and it's never the manufacturer.
I mean, scribe line, mule shoe line. These are all things that you should probably have other people looking at.
I 1,000% agree. So again, then we get into like just the image acquisition, right? What are the standards for this? Do you use a cell phone camera? Do you require a certain signal to noise ratio on your CMOS? Do you require universal shutter versus progressive shutter so that you can make sure that you're not getting things? How do you manage reflections? How do you manage nighttime things? And then how many pictures do you need? Right? Do you need just a picture of each blade? Would you like to see the top of each cutter? Would you like to see the back side of each cutter so you can evaluate erosion around the pockets that the cutters are in? And if you see comments that you'd like me to respond to,
no, keep going.
And so
if you see any that you want to, feel free.
We'll do that. Take a robot and teach him photography. Elon's working on that, I think.
Yeah.
And Dr. Theodore, you always has great comments. Thank you for your comments here.
That's one of Theodore's either students or works with him. So
yeah.
Wait.
Yeah.
Click back over here.
Yeah.
There we go.
So then you think about the timeliness of this information, right? If I want to use the information from a bit grade to select my next bit, I have to have that in a timely manner, right? So because it's off critical path, it's unlikely I'm going to get it. I would like to before they're making up the next BHA, say, here's the next bit I want selected of what's available to me, or here's how I want you to run it, so that we don't have that happen again. Instead, we have very crude grade that's done on the rig. If we want a better grade, okay, we're gonna have somebody come in a dually, pick it up, throw it in the back of their truck, drive it to the infield warehouse where a slightly better grade can be done. And then if it's like a critical job, or it's an offshore job where we really have to focus on the science of performance, hey, I got to get that to an onshore facility, right? That all takes a lot of time. It can take, this whole process could easily take 7 days to get a really high quality grade. And you think about the handling of this thing that has to occur, right? Now you're asking multiple people to touch it. You're putting it on trucks, you're loading it and you're unloading it. And so we wanted to take away some of these opportunities for delays and for injuries and things like that. And then we think about just the information that I can get from a handheld camera on a drilling rig, right? Back in like 2014, 2015 timeline, and it's still out there, but this was kind of how it got started. There was a contest called Kaggle, and Google was a big sponsor. Other companies were a big sponsor. And the idea was take the pictures on the internet and have a computer be able to say, is that a cat or is it a dog, right? And cats and dogs, they have noses, they have eyes, they have ears, they have mouths. So these like basic features are all the same. And eventually, it took some time, and the Kaggle contest got to like super high accuracy of being able to differentiate between cats and dogs. Now they're to the point where they can say what species of cat or dog, which is really, really great. But what they had at their advantage was essentially, I'm only trying to determine one or two things, cat or dog. And I have an essentially infinite data set, right? On a drill bit, we have the inverse of that. I am trying to differentiate measurements, properties, characteristics, all kinds of things about, hey, Clint Moss, how you doing? I haven't seen you in forever. And Aaron Eddy, Carrie Eddy, okay. So it's the inverse problem with drill bits, right? I have how many pictures, the best company in the world, let's say, and I'm not saying they are or not, but I know Paul, and I know he takes lots of bit pictures. So I'll say EXXON maybe serves as the paradigm of all this. How many bit pictures they got? How many of them are 5-blade bits with PDC cutters versus 7-blade bits with TCIs or tricones or whatever, right? We're trying to differentiate so many
shaped cutters.
So many distinctions with a much smaller data set. And then how many of those people are actually putting those images into a Kaggle? And how many of them are tagging them before they put, because every one of these was cat or dog, right? Because like everybody just snaps a selfie with their cat, me and my kitty, it's like, so it's tagged automatically. And so these images will come, they're not available. And so like we're trying to solve the problem without solving the basis of the problem first. So I said, we need to rethink this, right? Writing a manual to teach a guy how to snap pictures of a bit isn't sustainable. It's not going to accomplish what you really want it to accomplish. And then even if it does, as soon as you have a lapse in organizational discipline, you're starting from ground zero all over again, right? So what we want,
filled way.
Yeah, it's lather, rinse, repeat. And so we said, let's start with some key principles in place, right? So number one, I want to take the subjectivity out of grading, right? Because that, for me, that slowed down my work as an engineer and as a data scientist, right? But I have to do it in such a way that people trust it. So it has to be at least as good as what we're getting now, which thankfully wasn't very hard, because what we're getting now just had so much variability, and just reducing variability would solve a huge part of the problem. The other thing is build the data so that I can always join it very easily. Me joining this bit grade data to a time series data set was not fun, right? The way we're doing it now, it explicitly ties it, and anybody can do it. And you don't even have to have like an expensive WellView system or something like that. You could do it with simple files that you can put into any database, and because of the way we're giving it away. Then we said, okay, let's make sure that the original IADC dull grading was around tricone bits, and they kind of adapted and modified it slightly to take care of PDC bits. But I don't think that those are going to be the only kind of bits that we ever use. So we should have a way of doing our work and describing bits and collecting data about them that could handle any kind of mechanical rock cutting device on the end of drill pipe in the future, right? We should make it so that the data isn't, contained in a proprietary application. So if you really wanted to follow this process with, a magnifying glass and a person who you trust, it should be the exact same data collection and data model as if it were done by machines and computers and all of that, right? And that way, if another machine comes along in the future, or you have some super brain that is the best at grading bits and everybody sends them to him, whatever, we don't care how the data gets there, and it should be independent of that. And then lastly, these sort of things only work if everyone's using them, right? It doesn't do anyone any good. EXXON or Chevron or anybody could build the best bit grading thing in the universe, but if they're the only ones using it, the bit manufacturers aren't going to, redesign their factories just for EXXON, as much as EXXON would like to think they will, right? They can't, right? So everyone has to be using this and talking in the same way. So we said, let's start with that. And then I said, look, I'm a simple guy. I don't like overly complex things. They break, and then I got to fix it, or I've got to try and understand somebody else's complex thought process. And it's frustrating to me. So I said, when I was at Chesapeake, I saw the manual, took those 42 pages. I walked down we had a nice photo lab at Chesapeake. They had lots of really nice things at the time. And I said, look, I think this can be done differently. I got a GoPro, I got a tripod, I literally stole a turntable out of a microwave in a break room. And I went into one of the floors that had a fiberglass bit on it. And I just set up this little thing. And with the GoPro, I was turning the bit, and I recorded the video. And I said, look, this can make a 3D mesh. We made a 3D mesh. We showed that we could do it. And I said, now, if we are willing as Chesapeake to either, take a dive into this or invest in somebody to build this technology, we could burn this 42-page document and not have to train 700 people. And we could focus on moving our rigs faster. We could focus on less spills and emissions, right? Things that are honestly more pressing, right? And, fortunately for me, and unfortunately for them, they said, we're really not interested in that. So I kept the IP. And what that led to was we made a device, right? Made a device that we could put a bit on, put some really great cameras in it, had some really great lighting. One of the hardest problems we had to solve, and by the way, we have a patent on this, US 11,582,393. We had to solve just reflections off of cutters. It's brutal. These things are polished diamonds and they reflect light very well. And so we had to do that and to deal with some of the issues with, super high contrast and deep shadows and things like that. And so we solved all those problems. And then we had to figure out, where do we draw the line? All right. So how do we want to be able to compete with a good human grader, right? I can do this fast, I can do it cheap, and I can do it well, but I can't do all three. So the first thing we tried to do was cheap. Built a really simple device, literally with a blue barrel that holds chemicals at a car wash, because it's a blue background. I can take it out. It cost me $50, right? That got us to a certain level of confidence and accuracy in our grading. And it was a great way to start with very little money involved. And then we said, but that doesn't get us to quite where a human's at. So we had to invest in better cameras. We had to invest in better control of the position of the things, until we could get really high confidence meshes that we could then turn into really high confidence analysis. And so we're doing that, right? What we're getting now is picture quality that you can't even imagine trying to get from a handheld camera on a drilling rig. And what this means is we're starting to get into the 1 or 2 thousandths, right? So even the guys in the lab probably don't have micrometers that can reliably trying to like, hold it on an odd shaped cutter or across a damaged area, they probably cannot reliably and repeatably get as accurate measurements as we can off of these. And, we chose cameras on purpose. There are some folks out there doing this with lasers. We get better resolution than most of the lasers, unless you're going to spend like $100,000 on a laser. I mean, you got to spend a lot of money on a laser to get better than what we're doing here. But also the lasers don't return color. And if you're trying to do erosion and corrosion, color is really important. And also just for cost, right? If somebody were to walk off with one of these devices, which can happen, or if someone were to, I don't know, drop a drill collar on it or whatever, prison ready design.
Stranger things have happened in the oil field.
We want to make sure that, we wouldn't be too bummed out if we were to lose an entire device, or if someone were to harvest it for parts or something like that. And so the lasers were, just like price wise, and just the controls of them were more complicated. And then also I have a lot of variety in vendors, and as camera technology improves, I can benefit from that, where, I don't know how much more the lasers are going to get, but, so we can benefit from future advancements. But that was the idea.
Yeah.
And then we built a workflow behind that. So we actually built 3D meshes out of that, and we're not analyzing the whole thing. The first thing we do is we break it up into pieces. I identify what part of that mesh is a blade, what part of that mesh is a junk slot, what part of it is a cutter, right? And so now I can send each cutter off to its own little process. I can send each blade off to its own little process, right? And then I can break each blade into a logical zone. So, we have nose, cone, shoulder, gauge. What if I wanted more? What if I want different ones? What if we as an industry decided we wanted to break that up? Or what if we said we didn't care about that anymore? What if we only cared about, radial position? What if we only cared about, different properties of the cutter? We could describe them in different ways. And so, we started breaking these things up. And the cool thing is, as a user, that provided some benefits, because now I don't have to pull up a 2 GB mesh and put it into, some browser where I can see it. If I only want to look at a blade, okay, that's a lot smaller of a mesh. Just show me the blade that's damaged. All right, awesome. Show me the 3 cutters. Click, click, click. And so if you're in a low bandwidth environment, or just, you don't want to spend 18 minutes downloading a 2 GB mesh, it provides benefits from the user.
Or if you want to be able to just email it.
Yeah. Some of them you absolutely could. And then we started thinking about measurements, right? So not only am I taking these things discreetly and breaking them up, but now I have a thing. Now I can measure it. And then we can put all of that data into a database that I can query, and I can join to other things. Now, does it have to be a relational database? No. In fact, we're doing some other things with IADC and others where we don't want this to have to be put into a relational database, right? You shouldn't have to spend any more money than you want to get this done. So yeah, each blade and mesh has its own cutter, which is awesome. We would look at the cutters, ideally, and this is something else that comes into play. Have you ever seen anybody grade a bit before it goes in the hole?
No.
Right. Why shouldn't you? Right. And in fact, that's a really good idea, because if you order a bit and you didn't get what you ordered, how do you know that? Right. I ordered 18 millimeter cutters and they sent 17. And is anybody going to notice that by eye? Right. Or if somebody sent, and by the way, if I could have any influence over you all, stop having your bit manufacturers paint the bits. Right. Yeah, it looks pretty when it shows up, but it can also hide a multitude of sins. Right. So if you get a bit on location that is clean and hasn't been painted, you scan it first, you can tell if there's like damage to brazing. You could, so you would have a record of before use, and you would understand, was the damage caused, was that erosion caused because there was bad braze in the pocket, or because I just beat the shit out of this thing? Pardon my French.
That's right.
But also for, shaped cutters, or for cutters that, have profiles on them, that's a really hard thing to describe before you run the bit. But if you scan it before and you scan it after and you line those things up, it's really easy to measure how much of this does not exist anymore, right? And so that's what we were doing. We were extracting the befores, extracting the afters, overlaying them and saying, what's the difference, right? So now I can give you to 3 decimal places what percentage of that cutter face or that cutter edge has been affected, rather than just, between 25 and 37.5%, right?
Wow.
The other thing we did is we said, okay, since we're doing this, we can add some additional concepts here, right? I can give each cutter coordinates. I can talk about their angle of attack. I can talk about their relative position. The IADC dull grade does not consider primary, secondary, tertiary cutters. It's cutter. It's on the cone. All the cone cutters are the same, according to that grading methodology. We say, no, a cutter, if you have damage to your backup cutters, maybe you have whirl, especially if the backup and the primary cutters have the same damage and it's on the outside, right? You're probably, doing something that's different than if you had damage otherwise, right? Also, the IADC dull grading, kind of makes this simplifying assumption. It's not even explicit, it's implicit, but all the cutters are the same. And all the cutters are probably like circles, right? And for a long time that was true. It's definitely not true anymore. And also because we're taking these things and I'm extracting a cutter, I can say now a cutter has like regions, like a blade does. A cutter could have, be cut into quadrants, and I'll talk about that in a minute because we do that in a really neat way. And I can talk about its edge, where that is not included in the old dull grading methods. And again, now I can look at, blade. I could say, hey, this blade saw a 3% reduction in its volume. Like, okay, what's going on? Like, we really can't describe blades with the current methods. And then, how do we describe the diameter? We put a ring over it and find the one that doesn't fit, and that's the OD of our bit, right? I could measure the profile to say, is the bit straight? Is it got concave wear, convex wear? Is it eccentric? So did one side get worn out because it was whirling against the borehole for a long time? Just things that you could not possibly describe. Now we're saying, okay, because we've thought through this and we have new ways of doing thinking, let's build a data structure that captures this. And we spent a long time thinking about this. Things I can't even do right now with the AI and the machine learning, we have reserved spots for in the data model because we know one day we'll be able to do it, or a human with enough time could do it. And so we're trying to be mindful of that.
Nope, not right now.
I turned that off too. Like I said, so this is an example of how we are looking at just the radius. Each blade has its own radius, right? So I could do it, element by element. Here's how we've trained the models to identify primary versus secondary cutters, and we can identify them as such. If there was a third row, fourth row, a 99th row, I don't care, right? And where could that be important? Well, when you're trying to identify the alignment of impregnated, diamond impregs, right? And maybe there could be some discussion about the orientation of those and the placement of those, right? And with a method like this, I could describe them all completely. Like each little diamond is the equivalent to a little cutter. And then we looked at, again, this is how we are separating the side of the cutter from the face of the cutter, because now I can look at erosion and corrosion on the side. I can look at, did a chip or a spall begin at the side, or is it, from impact on the face, right? Right now, that's not possible with and then I can measure the radius of each one of these, right? And say, did you get what you paid for? Did it come out the same as it went in? Then we said, okay, if we're going to describe a cutter and the damage on a cutter face, this has to be done in a way that makes sense and is absolute and would apply to a cutter in any position anywhere on the bit. And so I just borrowed some dentistry lingo, right? So, because your mouth has teeth in it that are like cutters, and technically they are, and you can describe their positions, right? So I have a superior row of teeth. I have an inferior row of teeth. The bit has superior cutters, the ones that are closest to the nose, and they have inferior cutters, or an inferior portion of a cutter, the one that is closest to the threads. and then distal and proximal. So proximal being closest to the center and distal being furthest from the center. What that lets me do is describe cutter damage in a vastly different way, right? So old IADC method, I would say, hey, the cutters on the nose are worn to 3. Awesome. How, like 11 cutters are all worn to 3. Great. But with this new method that we donated to the IADC, I can say cutter number 1 is on the nose region of blade 1. It's a primary cutter, cutting ordinal of 1. It has 2 types of damage. So it has chipping damage. It's on the distal portion of the face, covers 50% of the affected area, and it has a severity level of 2 out of 5, right? That is just music to the bit manufacturer's ears, because that is infinitely more data than they had before. And if they could get that level of analysis from every bit, they're going to turn you around faster, better bits, in faster than you can imagine, and they'll be able to repeat success a lot more, right? Or I could say it has thermal damage. It's on the superior proximal side, so superior proximal, upper left-hand corner, that quadrant, and it has a certain severity level, right? So now I can describe things in a different way. And then we started another project that, while it wasn't necessarily intended to be a part of this effort, it actually has become part of this. So Mark Anderson, a shout out if you're on the stream. If you're not, I know he's been a guest on here before.
Great guy.
A real mentor of mine. Can't say enough good things. He put together a project he called Stupid, because he was so tired of trying to share data with operators for his auto driller set points, and everybody gave him a different spreadsheet, and he said, this is stupid. So he made a project called the Stupid Project, which is like stop typing unnecessary process information down or something. It was an acronym. And so
he's a clever guy.
I know, I love it. And so that started with auto driller set points, but we said, we could also just encapsulate what we did for the drill bits. And so now you can actually, shout out to David if you want a link. I'll send him the link and he could send it out. This is open source. You can go get this right now. You could start grading your bits using this convention today with an Excel spreadsheet. And then what we're going to do is it's going to have a little button in the upper right-hand corner that you can see. And you click on that and it'll create a JSON file that you can send to anyone. And with a JSON file, your IT department could scrape it and put it in a database. You could make a collection of JSON files themselves into a database, but you're on a new standard and it costs you nothing.
So for those that don't know, like a JSON file, you could kind of familiarize with like an LAS file.
Yeah.
Right.
Yeah.
It's got a standard format for the information that's going in there, the placement and the tags with it.
Yeah.
Right.
Yep.
So you can essentially create the same thing for drill bits.
Yeah, and not could we have.
Okay. Yeah. All right. And we're all. I should say this, that there is a group that's working on the same thing for BHAs.
We're actually absorbing that into Smart and open sourcing it, and we're going to create the automated spreadsheets. And then if an IT department wants to build a fancy UX around it, great. And if you just want to use it and get going, or you're a small operator and you just don't want to spend the money, it's free to you to use right now, and you can get the benefit. So. We're actually, I'm meeting with the guys at EXXON to kind of start doing all that work for the BHA stuff. And we got the IADD, they sent us over their stuff. So we're just going to incorporate it all. And ours is a GPL3 open source. So anybody can use it. You can put it in commercial code if you want. You just can't make money directly off of it. And if you improve it, you have to give it back to the community. So again, so I think, in this project that we put together, we kind of addressed all of those initial goals, right? Drive user adoption, make it universal, respect the people and automate it when you can, and give people a better way to analyze things. Just want to give some special thanks. The folks at NOV and Read Hycolog really just gave us a lot of time to work this out. They let us take pictures of so many bits. So many types of bits. Matt and Tom over there. Isabel, she was at the University of Texas. She helped me on this. This actually started out as a joint university and commercial project. And, Brett Ludy at Teradata, he was my boss, who just kind of was a bulldozer for us to let us. I told you earlier, Teradata had no business doing this, but they let us do it anyway. And that's really because of Brett. I would love to answer questions, kind of see what the community thinks. And again, I'm not promoting, I hope you've seen in this, I'm not promoting any particular commercial solution for this. There are several out there. I think the method and being consistent about doing it is the most important thing.
Awesome. All right, guys. Well, if y'all have any questions, feel free to throw them into the comment section now, and we'll start kind of going through with them. And so here, I'll put us back over here like this. So then where are we at currently? Like, how many organizations have adopted this new grading? And like, as far as like, maybe a percentage, how many are doing the, some kind of X-ray, laser photographs, imagery of the bits to be able to do the grading? Because I know that there's several out there.
Yeah,
I've seen some that are just like, hey, take a picture with your cell phone and it'll grade. There's the box. I've seen a whole bunch of other solutions.
There's a few, and I would say the general answer is not enough people are doing this.
Okay.
And I think we've seen some hesitancy to adopt, largely because they want perfection day one, right? We want this to be 100% correct all the time, and if we disagree with it, then kick rocks, right? That's not the way you bring new technologies to market. You gotta let them mature. You have to let them grow. There has been this pushback that, our bit manufacturers should grade our bits, and if you want to get overcharged for your bits, or if you want there to be lots of contention or the opportunity for conflict, go ahead and do that, right? But I would strongly recommend against doing that. And if you got your supply chain people involved and they're good at what they do, they would tell you, don't ever do that. And they'd even probably write it in contract. Don't let your manufacturer grade their equipment.
Okay.
There are a variety of approaches to this. There are the cell phone methods, which I tell you, they get to 80% real fast, right? There's some work done in the universities where they're using convolutional neural networks and kind of open sourcey things. They get to 80% confidence real fast. But to go from 80 to 81 takes more work than it took to get from 0 to 80, right? And it stems every time from the fact that the images are of insufficient quantity and quality, right? You got to have a lot of pictures. They have to be right. They have to be good. And
I think that was a comment on here from Andres who says, we found out that we need 120 pics at minimum.
By the way, that's my system that we designed. That's exactly what we settled on. We tried to do 90. We tried to do 360. 120 was a real sweet spot for us in terms of speed and, the cost benefit of getting 3 more pictures. Just the incremental improvement was very marginal, like less than 0.5% kind of improvement. And so our thought was, we'll just wait for a better camera and then keep taking 120, right? And then maybe better cameras will get us down to 90. But for us too, we said, there is a time bound where, like somebody's willing to handle that bit to put it in the box and press a button and walk away, but that can't be all day. It's gotta be limited to where they're, going to be able to take it out and get the bit down where it's got to go and stored and put in a box and sent back to town. So we're trying to do it in like 10 minutes too. So if you take too many pictures, it can take too long, or God forbid, like 120 high-res JPEGs even, or RAW files, because we use RAW files. 120 RAW files, you're talking a few hundred megabytes of pictures. And that can be a lot for a rig comms, right? So again, we didn't want to overwhelm any part of the system.
So is there the possibility of being able to load the SolidWorks STL file into the system and say, like from a modeling perspective, because like all the modeling stuff is probably is going to be done off of the perfect SolidWorks design, right? Then how it gets manufactured, there's going to be discrepancy there, and then obviously after it comes out of the hole. So you talked about being able to grade the bit before it went in hole. Is that portion also considered into the mix to be able to say, okay, look, this is what it was designed to, this is how it got to the rig, and then this is what it looked like after it came out of the hole, and this is like how big of a variance there was in each step?
I can say, I can't give a ton of details about it, but I can say that we were working on that with NOV. I think Torex, they have their own laser scanner, so they're probably doing some of that internally as well. The big problem with that is, and it goes back to like developing this technology and getting it to market as well. One of the reasons that it hasn't been done as quickly is because Schlumberger can't do this. There is a 0% chance that Smith is going to give Schlumberger their design files for a bit. And in fact, Smith would prefer that Schlumberger doesn't put their bit in a Schlumberger box, not Smith, but like security or whoever, Smith is Schlumberger. Because that's essentially gives them enough information to immediately reverse engineer their bit, right? And so I think this can't be done by, this can't be provided by a bit manufacturer or a company that owns a bit manufacturer. So that really narrows the field of who can deliver it. And those companies just aren't, huge multinationals. They're like literally 2 mom and pops, right? That are like trying to get funded, trying to get this out, doing their best, and just waiting for the oil patch to go, yay, it's perfect, we'll all pay for it now. It's like, well, you're going to wait forever unless you throw a few dollars at it.
Yeah. Everybody's in a hurry to be second.
Yeah.
Nobody wants to be
a lot
first
of
with
that.
it.
And let's be honest with ourselves too. Drilling engineers are a fickle bunch. They don't like seeing things that they disagree with, and if that's wrong, I can't trust you. And it's like, well, a better conversation might be, if that's wrong, let's talk about why, right? I mean, I was in a meeting with a large U.S. independent a couple of weeks ago, and we did some analytics for them, and they said those analytics are wrong. And I said, well, maybe they are, maybe they aren't. Let's look at it together and talk about why we disagree. And it turned out, their drilling rig had a known issue with their block position. And I can't give you good analytics on that data if it's bad. And like, it spawned this massive conversation with the drilling contractor because it was a systemic issue that they had to address. And it was, a lot bigger than that. So that's the other thing we have to.
Like, all your weight on bit numbers are wrong. Well, did we zero it right?
Like, why is your
No.
block? Why is
Well,
your
block
block
data
height
wrong, or is
yeah? Why is your block height minus 30, bro? Like, are you sitting on BOPs or what's going on? But that's a cultural mind shift that has to occur. That technology, you use it in the right time, in the right place, and you contribute to its maturity, right? And if we're committed to, as an industry, adopting technology, and we say we are a lot, that comes out of everyone's mouths all the time, and they beat their chests over it. But when push comes to shove and we say, it's time for us to materially and personally invest and to give it a chance to mature, the brakes are hit really, really hard. So as somebody that's tried to bring different technologies to market over time, I would say, like, people here who are listening, and I know we have some drilling managers on and some others, have real conversations with your team about that. And, think about investments in technology a little bit differently with longer terms. Very few technologies pan out at a quarter. Few technologies pan out in a year, and expect that there's going to be a certain amount of failure in investing in new technology. New stuff in Silicon Valley has like a 90 to 95% failure rate. But I think in the oil field, if we started just by saying 50-50, right? And if we accepted that as a possibility in our technology journey, we'd be a lot better off than we are now, because we don't even accept 50-50.
So let me ask you this. Let's go 10 years in the future. Where do you see the automated grading at that point in time?
I think it's on every rig. I think, there should be other automated grading on rigs as well. I think, we were working on automated, pipe thread inspection and pipe body inspection. These things just, especially as fast as we are just wrecking drill pipe these days, and there's a shortage of it, right? You probably need to have, like, as you're picking it up and laying it down, have some way to inspect it in process, right? But yet these things are going to become absolutely critical. Automation on drilling rigs in general requires a commitment to good measurements and metrology, number one, because you can't automate a system. You can't put AI on a drilling rig. You can't even turn AI loose on a car yet. And a drilling rig has way more complexity. So these systems need to be deterministic. To have deterministic systems, you have to have data that's trustworthy. So you got to invest in that. Then you have to invest in really tight process control. And then you have to invest in thorough inspection and evaluation of the process and the materials at a very regular intervals. And until you do all those three things, I know there's a lot of talk about automation on drilling rigs and robots and things like that. There's a reason that most of them have failed, right? The way I met Mark Anderson was an automation project on neighbors' rigs for Shell, and that automation project was like on the verge of being absolutely shut down. And it was because the factory didn't have good quality control over the manufacture of certain inertial components. And the drilling rig itself didn't have good quality control over the data that was being fed into the control system. We solved those two problems, and it took us like a month. And it went from like, this technology deployed and maybe working on 2 or 3 rigs to within 90 days, we had it on 90 rigs and it was working perfect. Right.
Wow.
And so I can speak from experience that if you don't solve those 3 problems, automate anything you want, and it's just going to automate yourself into disaster. I hope that answers the question.
I don't know. What do you see? Like, what other technologies do you think will come about because of this? Like, what else could this, this is, there's a bottleneck that's here, right?
Yeah.
What could this unlock? What's on the other side of it as people start to adopt this? So not only are, you look at the value that you're getting out of doing this, but what's the value that also comes after it?
So somebody is going to like take Fred Dupriest and Paul Pestusik and like digitize their corpus of knowledge. And not only will we automate like the image acquisition and grading, but we're going to be able to do some causal inspection as well, to say, okay, you caused this by doing X, Y, Z. And so this idea of, limiter redesign and fast iteration on process is going to be amplified so much, right, by being able to do just this. And then the next thing that's going to happen along with that is variance reduction, right? So variance reduction or process control is a necessary first step to automation. I do think this is a key component of automation going forward, right? And not just for bits, but for tubulars and motors and other things. And so it's part of that foundation that we want to build to get there. I want to see a day where there's, 2 guys that are really just like key to running the rig. Everybody else is maintenance and, and having an easier life, right? I mean, you've been on rigs, you've seen those guys, they go home tired, they go home hurt, they go home hungry. And the oil field is made for a special breed of man, or, the few ladies that are out there. But if we change the way the process is done and we give some automation and change the paradigm of that environment, we'll find that more people are willing to do it. The cost of labor will come down a little bit. More people will be exposed to it, and it'll change the way people interact with oil and gas.
So I want to go back to this because I want to be able to make sure I'm tying this in correctly. So we take, these beautiful 3D mesh images, this, electronic, automated dull grading, and then be able to hook that essentially back to the EDR.
Oh, yeah.
And be able to say at 5,500 feet, as you were going back to bottom, you either did it a little too fast, a little too slow, and that's what caused.
Yeah. Or, here's a secret. And the other thing is too, our materials are so over designed that it's almost never one event that actually causes something to break. It's usually a sequence. And I think we'll be able to start identifying those sequences, and we'll be able to stop them before they cause catastrophic damage. And then what we may find as well is that if we're able to look at those sequences, predict them and avoid them, if we were able to reduce the design factor of some of our equipment, then that becomes cheaper. Or we can turn those design factors into HPAT design factors, or other things that get us to where we want to get for geothermal or for other extended reach stuff.
All right. So now here's my setup to this question. If we can start to tie that back, then in essence, it could be possible to grade the bit before it gets out of the hole.
I think there's a distinct possibility that now it would be a coarse grade, right? It would be like, I expect damage on the inside or on the outside, and I expect it to be roughly this much.
Yeah.
I would wager that, there are some people that could probably do close to that already today.
That would be so fun to see.
Yeah.
All right. If you're
yeah.
working on that, let me know. We'll have you come on the show.
That'd be awesome.
100%. 100%.
Yeah.
I don't care.
Call Pradeep.
It could be as commercial as it wants. I still just want to see it.
You had Pradeep on here from UT?
Yes.
Yeah, I wouldn't be surprised if he had somebody working on that bit.
Okay, here we got a question here. So, what role do you see at bit sensors / vibration data to support increasing longevity of bits? From LinkedIn user. You can throw another comment in if you want your name thrown up there. We just don't know.
Yeah, so that's a great one. I do have experience running those tools. And I'll say I think that technology is very important. It's underused, but there's also some care and feeding that comes along with it. So when I was getting these from Baker before, I actually went and visited them, and I said, let's tear one of these down. Let's talk about firmware. Let's talk about how I manage this, how the data is recorded, and all of that. And what it was clear to me at the time was that, and again, this was years ago, and things have changed since then, is that these were designed for laboratory testing and to gather data for, like, the lab knew what they were doing to that bit. And so they would have an event that they planned to initiate, and then they would record data around that event. I think we're trying to do the inverse of that with these near bit at bit sensors.
Oh, okay. Morgan wants recon logger.
Yeah. So I think, we have the inverse of that. So I think there needs to be some conversations with data scientists, like, about how this data is collected. The data sets are very large. They require signals processing and time series stuff, which is complex. And so there has to be real planning put into how you're going to manage that. I can tell you right now, like, no one's doing it very well.
The other big issue there that, from my personal experience of having, worked with this kind of data, is connecting everything back to surface.
It's so hard.
So you're trying to connect 1 hertz data to, let's say 500 hertz, 50 hertz, 100 hertz. Like, it's orders of magnitude greater in the amount of data that you're getting downhole than you are at surface, and trying to match those two up to one another. And then throw on top of it, like, the thing that we talked about before, which is, like, somebody doesn't zero out the weight correctly.
Yeah. Yeah. So metrology is super huge here. And I'll give you 2 things to consider. One is that in a rotating inertial reference frame that the drill bit is in, it is closer towards the center of the earth. So its angular acceleration is different, a fair bit different than what's at the surface. And it's also got its own rotational frame. So believe it or not, time is different. Relativity tells us time is different at that location than at the surface. Now, it may be a small bit different, but over the course of days, there can be drift because of that. Then these are electronic instruments where clock performance is a function of resistance and temperature. And so you take this at the surface and you have 1 clock speed, and you put it in a hot environment and it has a different clock speed. So you have multiple forms of drift inside of those instruments. And so you have to be able to compensate not only for drift, errors at the surface, and then trying to align instances where you have known, so you can line them up. Because also the downhole stuff isn't continuous. And so it's usually recording in bursts and things like that. So it's really, really hard. I have worked on that with some very large service companies and to try and help them solve that. Super complicated problem. I mean, you're bringing in, like, the guys that plan, like, the trajectories for satellites around Venus and going to Jupiter. Those are the guys that you got to bring in to solve that problem.
Quick story, because we're talking about the timing with these. I was working on a project once where it was another vendor that was working with an operator. So it's, 2 vendors kind of working together to help the operator with some of the downhole data. And the guy told us, he's like, all right, I need you guys to have, X level of certainty on your time across all of the tools that are downhole. And at first, when he said it, we were just kind of like, well, we can get as close as we can, but, this would take a significant amount of work to be able to get there. And then one of the guys back at the office, I'd sent them an email saying, hey, what do you think about this? And then he starts looking it up, and the timing that the guy was requesting, because he just kind of said it to me, so I didn't have any frame of reference. And I get a message back from one of the guys at the office. He's like, yeah, he's looking for greater time control than what the hardened collider is using for smashing atoms into each other. So I was like, oh, okay, yeah, sure. We're not getting that done.
It
was like,
I wrote a little book, a little, handbook, and I gave it away to the operators group for data quality as like a primer on metrology for drilling rigs. And in one of the sections, I addressed time measurements. Right now, I don't consider myself an expert, but I have learned enough to know what I know and what I don't know. And I can tell you that timekeeping itself is a very deep science, right? And being able to synchronize any class of devices and then put them in a well bore, if you can get them all to be within a few seconds of each other, you're probably doing good, right? Let alone like if you're looking for sub-second or anything like that. And
hundredth of a second.
Yeah, laugh at that one and go about your day. But there are signals processing approaches that can resolve those issues, especially if the functions are smooth and continuous. And these are approaches that have been used for decades in other industries. You can stretch and you can compress these signals, and because all the information is still there. It's just when it was sampled is a little bit different, and you can fill in the blanks and you can do things that would make it appear to be within 100th of a second. And for all intents and purposes, for analysis, the error would be small enough you wouldn't even be able to tell. Anyways, we could go on for a while about that one.
Yeah. All right, guys. We'll wrap it up there. We've already gone over an hour and whatnot. Nathan, thank you so much for being on the show.
Thank you.
All right, one last thing that we need to do, everybody, let's remove that one. Stop screen share, present, share screen. This is what everybody tunes into the show for, right? Chrome tab. There we go. Giveaway tool. That's the one I want to share. Why is it not letting me do that? Okay, cancel. Screen share was canceled. It's not on cancel. Okay. Okay, present, share screen. Hold on. Come over here and do this. What did I do? Chrome tab. Yeah.
Just click right on it. There you
go. Oh, that's why. All right. My bad, guys. Good thing Nathan's here to be able to help me through this. Oh, did I? Oh. It killed it. Uh-oh. We only have 4 entries now. Whoops. Sorry, guys.
It is an MWD issue.
Yes, it's okay. Yeah. Thanks, Eric. MWD issue again, Dave. Yeah. Yep. Excellent show up until that point. Very interesting downhole time. Enjoyed this. Thank you. Yeah, so I think I'll have to follow up with Charlotte. I think they're working with 3D printing drill bits.
Yeah.
All right. Let's add this to the stage. I apologize. All right. There's not very many entries. So like everybody else that put in hashtag KeyDrill, I really, really, really do apologize.
Do it again. We can watch the number go up.
Yeah. So yeah, here. I'll give everybody about another minute. Tell us what projects you're working on right now.
So right now I'm working, VP of engineering at WellDrive, trying to build that company out from a product to a more general services, data management and analytics company. I'm contributing to IADC and SPE. So trying to take these concepts around understanding of data and like democratize them. So you'll see a lot of that coming out. And then I just joined the board of advisors for a company called Blue Clarity. And so we're going to help use insurance to lower the cost of insurance for control of well and other things, and also use that to help encourage really good practices on the well control and safety side.
Awesome. All right. We've got a handful more entries here. Let's see. Okay. Yeah, we're up to 11. So we've at least doubled it. All right, we'll throw this back up there on. Oh wait, no, it's already up there. So there we go. So we're up to 12 now. John DeWort got in there. All right. So 5, 4, 3, 2, 1, and we'll hit the drawing. So sorry for everybody else. I know we were already up to like 20 something. My mistake. I apologize. But this week's winner is Prabhat Shukla. Prabhat, thanks for tuning in, watching the show. Send me a message. Send me a LinkedIn DM. We'll get address and we'll get Tracy to be able to send you some stuff over.
Charlotte, look me up on LinkedIn. I'll get you connected with the people that are doing it.
All right. So we'll take that one off. Once again,
hey, thank you.
Thank you so much. Do appreciate it. Everybody out there, I hope everybody has a wonderful, wonderful weekend. It is the holiday season for Christmas parties and such. Please be careful out there. Get home safe. Don't drink too much.
Or drink just enough.
Hey, whatever. Have a DD. Call an Uber, right? If you need somebody to help you out, just do that. Let's not have any tragedies over the holiday season. I'm trying to think of anything else. We've got another show up next week. We've got Mr. Ben Jeffries, which will be the last show of the year, and episode 150.
Wow.
For anybody that's been paying attention and counting, Tracy has. Episode number 150 of the Vidor Locksmith Show. That's happening next week. So we're going to have a kind of a big giveaway. KeyDrill is going to be the sponsor for that one. So we've got some extra swag from them. So you're definitely going to want to make sure you put in hashtag KeyDrill on that one. I will be sure not to screw it up. Next week, there was my technical difficulty of the week, and it was 100% my fault. So, all right, guys, that's it from me. Hope everybody has a wonderful weekend. Look forward to seeing you guys Friday for episode number 150. And as always, know your industry.